Okay, so let's do the same type of activity we did in class. And this time we're going to use let me get my pen here. We're going to use a 5,000 hertz signal. Okay. So let's think about how this will work. So here you have a speaker that is 90 degrees at a 90-degree azimuth, so directly to the right side of this individual facing forward. Okay. 5,000 hertz is a fairly high frequency, so it will have short wavelength, right? So let's think about first part, right? So 5,000 hertz signal, okay, it's traveling. Now, first thing we're going to talk about is the pinna. What does the pinna do, right? If you remember, pinna effect amplifies, kind of looks like this, in that 5K region, right? So it enhances that. But then, again, when you add the effects of let me do a different color. When you add the effects, and by lengthening, when you add the effects of the external auditory meatus, right, you get that shift down to maybe 2 to 3, 2 to 4K, okay, somewhere in that range, okay? So a 5,000 hertz sound it's got a little bit of emphasis, if you will, enhancement, based on the external canal and the external auditory system, right? Then you have the tympanic membrane, which vibrates 5,000 times in that second. Again, it matches the impedance of the air, the air molecules, to the impedance of the fluid in the cochlea. If we think about the basilar membrane, right, and how it's more, I'm not really good at drawing this, right? So you have the base, you have the apex, right? And essentially, this goes from 20K or so right at the base here to 20 hertz here. Well, that's not exactly correct. That's the audible region, and I think there are it goes a little lower. I'm not sure about higher, but in any case, that's the usable region for humans. So if we were to think about where along the basilar membrane this would be, again, this is just picking a spot, but it would probably be somewhere, obviously, towards the base, right? It wouldn't be over here in the apex area because it's a mildly high frequency. So that 5,000 hertz would excite somewhere in that region. Again, think about how the basilar membrane gets excited with auditory signals. Let's say this was the excitation amount of hair cells with a 25-30 dB sound. If we increase that auditory signal to, let's say, 75 or 80, what you see is it would excite even though the signal is 5,000 hertz, it's going to excite a larger region of hair cells because of the increase in intensity. Okay? And so let me look at my notes real quick. I want to be sure to cover everything here. So that's the cochlear portion and the excitation there. Let me see. So we did that, and then let's talk about the the localization part. Okay, now I'm going to add some central auditory systems. We'll do another one of these with adding central, but I want to be sure we're clear up to the sensory mechanism where we're at. Okay, so let me erase all this and talk about localization. So if you remember the two cues for localization, intraoral intensity or level differences, IID or ILD depending. Okay, that's the intraoral intensity. Then we have the intraoral latency or intraoral timing differences, or phase differences. Okay, these are the two cues, intraoral timing or phase. You could do this. You might see it this way, or intraoral level differences. Okay, make them all the same color. All right. So those are the two sets of cues. All right. Now again, we're at we're at 90-degree azimuth, and we're doing a 5,000 hertz, 5 kilohertz signal. Now, one thing to note, we talked about when a signal is at directly 0 and directly 180-degree azimuth, there are no intraoral cues, right? Because it's at direct midline, if you will, okay? As I said, that doesn't happen very often in the real world. We turn our head a little bit to get a little bit of cue that we need, okay? So another important point is that these intraoral cues that we talked about are greatest at 90 and 270, right? They're greatest at those frequencies because obviously, right, if we do this, give them some ears, a sound emanating from 90 degrees, let's say, will obviously arrive this side first and then this side. And it'll be louder over here than it will over here. Okay. And so remember, these intraoral cues are greatest at 90 and 270 degree azimuth. Okay. Now, 5,000 hertz tone. Remember, we talked about in class 1,500 hertz. Let's use as the cutoff for kind of high frequency and low frequency. When we talk about localization, let's just use 1,500 hertz as that cutoff. So 5,000 hertz is considered a high frequency. It has shorter wavelengths. Therefore, it's more easily deflected by the head, and that is determined by the size of the head, the neck, and all those structures, right? We called that the head-related transfer function. And remember, we use that mannequin, Kimar, to hold all these variables consistent when we do research, which is really important. Okay, so so for 5,000 hertz, you get a lot of diffracted information, okay, which creates what we call the head shadow on this side. Sorry, it's hard to draw with this keypad or touchpad, but the head shadow, I know everybody knows how to spell it. Oops. That's not what I wanted. Hold on. I don't know what happened. But the head shadow, now I can't make it smaller. So we'll just leave it like this. So the sound is emanating from 90 degree azimuth. A lot of it's diffracted. And so it creates this region of reduced intensity over here. And we call that the head shadow effect. Okay, so in this example on the right side, at 90-degree azimuth, the right ear, you have a substantial difference in intraoral intensity, right? Phase doesn't matter as much for these high frequencies. It's more the intensity cue that's important. Okay. Now, if we had a 100 hertz tone, let's say we were doing the same thing, that 100 hertz tone would have longer wavelengths and would travel around the head easier. So intraoral less would be diffracted. So intraoral timing or phase differences would be very important for, let's say, a 100 hertz signal. Okay, you'd get less head shadow because the sounds would actually travel around the head easier, but you would have excitation of the basilar membrane, let's say, earlier on the right ear compared to the left ear. Okay, does that make sense? I'm trying to make this slide the correct size, but I don't know how I made it larger. But anyway, that's really what I wanted to show you and kind of go through, okay, this is what happens at this level, this is what happens at the next level, this is what happens at the cochlea, and these are the cues that we use. This is how the excitation occurs, and then these are the cues we use to localize sound. Now, when I give you information about the central auditory nervous system, we'll add in that component, like describing what happens after the sensory system and goes more to the neural system. Okay, so that's it for this example. Hope it was helpful.